Good morning, everyone. We're looking today at lesson 30.03, which is called Generating Electricity, and also we're going to study something called Lenz's Law. This is on page 6, I believe, of your lesson handout, and we're going to start off with something that's a little bit different. If we have a magnetic field, and the magnetic field you can see is directed into whatever you're looking at, and we take a copper rod, so this is a solid piece of copper. It's not a pipe, it's a rod. And we pull it at a certain speed, doesn't matter what the speed is, but we move it left to right through that magnetic field. It says in part A, use the right-hand rule to predict the direction of the magnetic force on each electron in the copper rod. So we've used the right-hand rule before, but not quite like this. So I'm going to highlight one individual electron within the rod. And don't forget, in the rod there are countless electrons because it's made of atoms. And copper, by the way, is a very good conductor. So there is one particular electron. If we want to find the direction of the magnetic force on that electron, we would have to point the fingers of our right hand into the plane of paper. We would have to turn our right hand so that our thumb is pointing in the direction the electron is moving. And I want to point out to you that the electron is moving in that direction because we're dragging it along with all the other electrons left to right by grabbing onto that conductor and pulling it. So our thumb is left to right. It's pointed to the right side of the screen or the page. Our fingers are pointed in, and hopefully you predict that the force on the electron will be towards the bottom of the page, out of the back of your hand. Now, the next question is, what does that, now all of a sudden I've switched to a collective force on all of the electrons result in? Because that one electron, which is negative, is forced out of the back of your hand, and that means that that electron is forced towards the bottom of the page, but every electron is forced towards the bottom of the page. So yes, there's a magnetic force on that electron, but all of the electrons are forced in that direction. So what does that result in? It results in the top of this rod being positive and the bottom of the rod being negative. And intuitively, this next idea should make sense to you, and it should also make sense to you using a formula. If I move the rod faster, the bottom will become more negative. Because when I move the rod faster, the magnetic force on each electron increases, so you'll be able to pack more electrons down on that bottom end of the rod. Bottom line, though, is what does this collective force result in? A potential difference. The top of the rod becomes negative, the bottom becomes positive, so you create a potential difference. A voltage. Okay, so this is the process that you use in an electrical generator. It's not as simple as just taking a piece of copper and moving it through a magnetic field. If you have a generator at home, it's probably a gas-powered generator. In a demonstration a little bit later, you'll be looking at some hand-powered generators. But a gas-powered generator has a little gasoline engine, and attached to the crank of the engine is a series of magnets that when they turn past coils of wire, and that relative motion of the wire in the magnetic field produces electricity. It produces a voltage. And the voltage that you create, the potential difference that you create, depends on three things. The speed with which the motion occurs, and that makes sense because if you increase the speed, then the force on each electron goes up because we know that the force is determined in part by the speed. If you increase the strength of the magnetic field, the same argument holds. We already know that a stronger magnetic field produces a greater force. So for the first and the third points here, increasing either of these increases the force on the electrons, which results in a greater potential difference. The middle one is just saying that if you have more material in the magnetic field, you're going to have more electrons being influenced by the magnetic field. So if I have more wire in the field, then I have more charge being moved, so I'm going to get a greater potential difference. If you now connect the ends of this rod to an electric circuit, then what you're going to actually generate is a current. You won't get really a flow of electrons until you connect the two ends of the rod to something that can carry a flow of electrons, like a light bulb. The current will only exist as long as you move the rod. As soon as you stop moving it, the force on each electron stops, so you get no current. And this process of moving a conductor in a magnetic field, or by the way, of moving a magnet relative to a conductor, is called the generator effect. I just want to repeat that last idea and paraphrase it. I can generate electricity by taking a piece of wire and moving it through a magnetic field that's caused by a magnet, or I could just put the piece of wire on a tabletop and take a magnet and move it past the wire. As long as there's a relative motion between the field and the conductor, you will get an electrical generation called the generator effect. Okay, what we're going to look at now is a very simple demonstration showing us the generation of electric current by using a coil of wire in the form of a solenoid and a magnet, which is going to be the source of the magnetic field. What we're looking at here is a solenoid. In fact, it's the same solenoid that we've looked at in class when I would connect a potential difference or an electrical power supply to the solenoid. We use this particular solenoid to investigate the magnetic field lines that were created around that solenoid. And we were using something called the motor effect when we were doing that demonstration before. We hooked a potential difference up that was taking electrical energy and it was converting it to mechanical energy. The mechanical energy, we saw evidence of that because when I put a compass at various locations surrounding the solenoid, the compass was deflected, so there was some mechanical energy that was being transferred to the compass needles. Work was being done to the compass needles. So if you connect a potential difference to a solenoid, you get an output of mechanical energy, and we call that the motor effect. Well, this time, though, what I have is I'm connecting the solenoid to what's called a galvanometer. And a galvanometer is kind of a multi-purpose meter. It's able to measure current and potential difference. So I have a little high-tech label there that I've clipped onto this. You can see that what we're looking at is equivalent to what I have on that piece of paper. So you might see that diagram on an assignment or in a textbook. Now we're going to investigate the generator effect. The generator effect says that if you move a wire through a magnetic field, you'll generate an electric current. You need to understand that rather than me moving the wire through the magnetic field, I'm going to keep the coil stationary and I'm going to move the magnet. So we'll start off just by moving the south pole of the magnet in, and you can keep your eye on the galvanometer needle, and while it's moving in, the galvanometer needle moves to the left, very, very slightly. When I pull the south pole of the magnet out, the galvanometer needle moves to the right. So when the south pole goes in, the needle is deflected to the left. If the north pole goes in, it's deflected to the right. So you have an opposite deflection. Now, we have learned that this current or potential difference that you're generating can be changed by varying a number of different things. One of them is we can use a stronger magnet. So I've got a stronger magnet now, and I'm going to move one pole in, we'll move the other one out, and you can see the deflection is greater. If I were to use an even stronger magnet, which is this big cylinder on this end, and I move it in, the deflection is even greater. Now I'll just let you know that we're on a scale right now where we're measuring current, and the scale is measuring microamps. So when I move this in, it looks like it's deflecting in or out. It looks like it's deflecting to about 30 microamps in both directions. If I want an even greater amount of current, then what I can do is I can get rid of this solenoid, and I can use a solenoid that has more turns of wire. So this solenoid here has 300 windings of wire. It has 300 loops of wire. And although it is a little bit of a smaller radius, it's a fairly large radius still. So I'll clip the galvanometer to the solenoid, and we'll go back and look at the original magnet, which was the bar magnet. And when I move it in, you can see that I get a considerable amount of current, a lot more than I did before. And that's because the magnetic field is acting on more pieces of wire, so more electrons are being influenced by it. If I want to, I can change the scale. Right now it's measuring microamps. I can change the scale to measure millivolts, because at the scale that I was at before, it was going off the scale, so I can't read it. So in terms of millivolts, when I move this magnet in and out, it's looking like around 40 to 50 to 60 millivolts, which is still a pretty small voltage. You certainly couldn't power a light bulb with that. I'm going to go now to the stronger magnet, and when I move the stronger magnet in, it's going off the scale now with the millivolt scale. So I can go to an even higher scale now, which is a 5-volt scale. So if that needle is deflected all the way to the edge on either side, we're talking about 5 volts. Well, you're not even going to get close to 5 volts. If I had to estimate, we're looking at maybe 0.2, 0.3, 0.4 volts. If I wanted an even greater voltage, then what I could do, don't forget there were 300 windings on this solenoid here. I can go to this solenoid, which also happens to have 300 windings, but you can see that the radius of the windings is considerably smaller. And that means that the wire that's being influenced by the magnet and its magnetic field will be in a region of space where the magnetic field is stronger. The closer the wire is to the magnet, the stronger the magnetic field. We're on the volt range here. Let's just see what happens if I use the regular bar magnet. It hardly moves. This magnet is not a very strong magnet, so we're going to go to the stronger magnet, which just barely fits in the opening, and when I move it in and out, I'm getting around, I would say, half of a volt. So hopefully that gives you an idea of what we're talking about here. With the generator effect, you have a motion of a wire relative to a magnet, and it's producing an electric current. Now let's take a look at example 1. Example 1 is just an application of this on paper. I've got a light bulb connected to a very similar situation. What we want to do is predict the direction of the current in the circuit when we move that conducting rod towards the bottom of the page. So again, I prefer to think about electrons when I do these kinds of things, because electrons exist. Conventional current is a fiction, it's a fable, it doesn't actually happen. So when I'll ask you to pause the video here and you determine the direction that the electrons in the rod will move. Hopefully, I just have to work this out myself. You determine that the electrons in the rod will end up moving to the left. You point the fingers of your right hand in, which is the direction of the magnetic field. X means in. You have to then turn your thumb so that your thumb is pointing to the bottom of the page. And if you have your fingers in and your thumb to the bottom of the page, the back of your hand is to the left. So that means that electron flow in this circuit is in this direction. And if you wanted to know the direction of conventional current, you would just switch that direction. So the electrons here are flowing, generally speaking, in a counterclockwise direction as long as the rod moves. Now what I'd like to do is compare something that we've already learned, but I haven't really mentioned it by its proper name very often. We have already learned about the motor effect. And in fact, everybody, whenever you use this formula, Fm equals QVB, or this formula, Fm equals ILB. Whenever you use those formulas, you're using the motor effect. The motor effect basically is the production of a magnetic force resulting from the motion of charge in a magnetic field. So specifically, when you have a current-carrying conductor placed in an external magnetic field, that conductor will experience a force. I'm really focusing here in this description of the motor effect. I'm focusing on the Fm equals ILB. I'm focusing on a wire, not a single charge. The generator effect, on the other hand, is when you take a conductor that does not have electrons flowing through it, and you physically move it through a magnetic field, you're going to generate an electric current. So the one on the left, which is called the motor effect, the wire has electrons moving in it at the beginning. And it's that flow of electrons that produces a force. With the generator effect, the electrons are not moving through the circuit until you move the conductor. So it's the motion of the conductor that creates an electric current or a flow of charge. With the motor effect, what happens is you convert electrical energy to mechanical energy. So you start off by having a wire that's connected to a potential difference. You're draining electrical energy from the system, and then the wire is forced so it ends up moving, and we call that type of energy mechanical. The generator effect is the opposite. You take mechanical energy and you convert it to electrical. So if you're ever watching an episode of the Flintstones and they explain to you how the microwave oven works in the Flintstones, there's an episode where the repair person opens it up and there's a little tiny dinosaur there on a treadmill. And the reason it's not working, by the way, is the dinosaur is tired. But when the dinosaur, the little bitty dinosaur, runs on the treadmill, that treadmill is connected to a series of coils of wire which move around through a magnetic field, and that mechanical energy from the dinosaur becomes electrical energy used to power the microwave. I want to draw your attention to some other terminology here. It's not really new terminology, but I'm going to talk about cause and effect. The cause of something happening always happens before the effect. So for example, I was baking last night and I dropped some eggs on my kitchen floor. Now I didn't just stand there and decide to drop them. Something happened which caused me to drop the eggs. And what happened was my dog ran in front of me. So my dog running in front of me caused me to drop the eggs. The cause was the dog running, the effect was me dropping the eggs. So causes always happen first. And in the motor effect, the electrical current is the cause, the effect is the force. In the generator effect, the motion is the cause and the effect is electrical current. So in the motor effect, current produces force, but in the generator effect, motion produces current. And that's a lot to take in. And before the end of this video, it's going to be even more to take in. Now, if you were to look at the motor effect just in general, I'm saying if you've got a current-carrying wire in a magnetic field, then you're going to have a magnetic force. That is about as succinct and to the point as I can get. The generator effect, are you moving a wire through a magnetic field? If you are, you will generate a current. When you look at the right-hand rules that we've been using, it appears that we have a separate right-hand rule for the motor effect. So you're looking at the diagram on the left, where the cause is the current and the effect is the force. And if the current is conventional current, it's out of the palm of your hand, but I don't really care about that right now. I want to draw your attention to the fact that in the motor effect, your thumb is the direction of the current, your palm is the direction of the force. In the generator effect, where you move the conductor and you produce a current, your thumb is the direction of the motion of the conductor and the current is out of the palm of your hand. And when you first look at these two, you notice something that can cause a lot of confusion. In one of the rules, the current is your thumb. In the motor effect, the current is your thumb. But in the generator effect, the current is out of the palm of your hand. Well, it's not really that you have two separate rules. In the motor effect, the cause is the current, which is your thumb. The effect is the force, which is your palm. In the generator effect, the cause is the motion, which is your thumb. The effect is your palm, which is the current. In other words, we can combine these two right-hand rules to simply say that in the motor or generator effects, the cause is in the direction that your thumb is pointing, and the effect is out of the palm of your hand. What we're going to look at now is how a simple DC generator works. So I have a loop of wire. The brown colored pieces are a coil of wire. And then I have at the top a light bulb, and I have two brushes. And the brushes are not electrically connected with a solid connection to that brown coil of wire. When we spin this coil, and you can see at the bottom that there's a crank, what's going to happen is that the coil will rotate, and if we rotate it in the direction shown, the wire over here on the left-hand side, the wire will be moving out towards you. But the wire over here on the right-hand side will be moving in. And if we use the right-hand rule to predict the direction of electron flow, I'm going to focus on the wire on the left. If I point my fingers in the direction of the magnetic field, and everybody should know that the magnetic field in between these two poles is north to south. So if I point my fingers in the direction of the magnetic field, and I point my thumb out, which is the direction that the wire on the left is moving, then the back of my hand faces the bottom of the screen, which means electrons will be flowing in this direction. If I go to the other wire on the right and I point my fingers left to right in the direction of the magnetic field, and my thumb in, which is the direction that wire is moving, then the back of my hand faces the top of the page, which means that the electrons on this piece of wire are going to move to the top. So the bottom line is, right now the brushes are in contact with this loop of wire. While it's in motion, that light bulb will light up. Now, a half a rotation later, and if you take a look at the bottom of the crank here and keep your eyes on it, this is the state of affairs a half a rotation later. And by the way, I drew that coil lopsided so that you can see that it is rotated from this position to this position. I won't bore you with the details here, but if you do the same thing now with the wire that's on the left that was on the right, you're going to discover the electrons are still moving down, and the electrons on the right are still moving up. And that's why this is called a DC generator. It generates electrical energy that we call a direct current type of electrical energy. And that just means the electrons are always flowing in the same direction. So as long as you are cranking this, what's going to happen is you're going to generate electricity. Now, you're not expected to know the exact workings of a DC generator, but I'm doing this because in a minute or so I'm going to show you a series of demonstrations using a DC generator and also a DC motor. So if you take a look at the screen here, what we've got is a DC generator, and this is a DC motor. And you'll notice a difference. The difference is at the bottom with the motor, there's no crank, because a motor doesn't need a crank. A motor uses the motor effect, which converts electrical energy to mechanical energy. So in the DC motor, this is the input, and the output is down here. This thing is going to spin. And I don't really want to go through the right-hand rule again, but you could use the right-hand rule to predict which way this will spin. But the bottom line is the input is electrical, the output is going to be a spinning of that shaft on the bottom. So you can connect that shaft to a belt to turn things. Whereas when you take a look at the generator, the input is down here, and the output is electrical energy. So there's that cause and effect thing again. And really, the point I want to drive across is there's not much of a difference between a DC generator and a DC motor, other than where the input or output lie. So now we're going to look at a couple of demonstrations with something called a Genicon. And a Genicon is a little handheld generator. Okay, what we're looking at here is it's called a Genicon. That's a brand name. What it is a little handheld generator. So when I drew the diagram of the generator in the lesson, I didn't draw it very well because I just wanted to get the physics across to you. I only drew like a single piece of wire. But in reality, we know that the more wire you have in the magnetic field, the more electrons will be influenced and the greater the potential difference will be that you generate. So in reality, that loop of wire is repeated. It goes around and around and around and around, and sometimes there are hundreds and perhaps even thousands of loops of wire that are all engineered together to rotate the same way through the magnetic field. And that's what's going on inside of this. There's a little generator inside. You can see it's the silver component inside. There are also a series of gears, and when I turn this, those gears take the coils of wire that are inside of that little generator and cause them to move very fast. If I want to generate a potential difference, then I can connect the output of this generator to something which can carry a current, and when I crank it, I get electrical energy out. Now, I'm getting electrical energy out of 2 light bulbs. I've wired these 3 light bulbs together the same way that things are wired together in your house. And things are wired together in your house so that you can turn some things off and still get others to operate. So I can turn on any number of bulbs I want here. One thing you notice is that if I have more bulbs going, it's harder. Well, you can't really notice this, but you might be able to tell from the sound. It's more difficult to get them to light up. I have to work a lot harder. Okay, one more thing I'd like to show you quickly here. The Genicon is being used as a generator in all of these demonstrations, but I told you a few minutes ago in the lesson that there's really not any difference in terms of how these things are built between how a generator is built and how a motor is built. Now, right now what we've been doing is we've been supplying mechanical energy as an input by cranking the handle, and the output has been electrical energy. But if that's how it works as a generator, I ought to be able to reverse the process and take a power supply and connect the power supply to the Genicon. And then I'm going to plug in the power supply. And you can see that what happens at this point is the Genicon is acting like a motor. It's an electric motor, and in fact, that's what's inside of it. If I want to cause the motor to turn faster, then I have to increase the amount of magnetic force acting on those coils, and I do that by increasing the current. And I can increase the current by going to a higher voltage, or a higher voltage, or higher, or higher, or higher. And eventually I'm at about 15 volts here, and you can see that what's happening is it's spinning quite rapidly. So the Genicon can act as a motor or a generator. Well, just a second though. If this Genicon can act as a motor or a generator, then this Genicon should be able to act as a motor or a generator. Which means I can use one of these as a generator to supply electrical energy to the second one, which should behave like a motor. So I'm going to connect these two together. And I will crank one of them, and you will see that the other turns in response. In fact, this is a very crude explanation of how a microphone causes a speaker to produce sound. When you speak into a microphone, there's a little tiny magnet in there that vibrates back and forth to the pattern of your voice. And what happens is that sends an electrical signal through wires to the speaker, where there's another magnet. Now the speaker's amplified, but the other magnet ends up moving in response, pushing air out of the speaker, and we call that air moving around sound. All right, so motors and generators are essentially the same kind of thing. Now we're going to look at something called Lenz's Law. Well, let me just read this through with you. When a conductor is moved through a magnetic field, a current will be induced in the conductor. We know that. That's called the generator effect. But now what you have is a wire in a magnetic field that's carrying a current. The wire that's carrying a current in the magnetic field is not carrying a current because it was connected to a battery, though. The wire in the magnetic field is carrying a current because you're moving the wire, creating a current. But a current-carrying wire in a magnetic field will experience a magnetic force. And Lenz's law says, and I'm going to explain this in a number of ways, that the produced magnetic force at the end of this series of events will always oppose the original motion. So if I try to move the conductor to the right through a magnetic field, I will feel something pushing back. If I try to take a conductor and move it through a magnetic field and I'm trying to move it through the ceiling, I will feel something pushing it down. The magnetic force will always oppose the motion. So if you move a conductor, you create a current, that current will create a magnetic force. Lenz's law says the force opposes the motion. So now I'd like to show this to you in a number of different ways. And there's absolutely no need to write it down. You could watch this video over and over again. I have a setup here where I have a magnetic field that is into the plane of whatever we're looking at. And I have a copper, big, thick, heavy piece of copper rod, it's solid, connected to a light bulb, and I'm going to move the copper rod to the right. I would like everybody to predict the direction of conventional current in that rod. Hopefully you say that the conventional current is towards the top of the page, because your fingers would be in, your thumb would be to the right, so the palm of your hand, which represents conventional current, is towards the top of the page. And what we have then is the light bulb that lights up because we have just reproduced the generator effect. We move a conductor through a magnetic field and we create a current. But now that current is going to create a force. And if I said to you, what direction will the force on the wire be? You'll point the fingers of your right hand in. You'll point your thumb up to the top of the page because that's the direction of the current, and your palm will be facing towards the left. So the direction of the magnetic force is towards the left. And I want you to note that the direction of the magnetic force is opposite to the velocity, the direction you moved it. And you can make up any orientation of fields and motions, and when you go through this process, the force will always be backwards. I want to point out to you that there's a series of 3 things that occurred here. The first was you moved it and it caused the second, which is the current. The second, which is the current, caused the third, which is the force. So from 1 to 2, the motion is the cause, the current is the effect, but from 2 to 3, the current is the cause and the force is the effect. So the motion causes the current, the current causes the magnetic force. And what Lenz's law says is that force will always oppose the motion. That's what Lenz's law is. That's one way that I can show it to you. We could take a look at a different situation where we're going to get rid of the magnetic fields and everything. If you have movement of a conductor through a magnetic field, you will create a current-carrying conductor in a magnetic field. You're going to generate electricity. If you have a current-carrying conductor in a magnetic field, you're going to result in a magnetic force acting on the conductor. That will be the result, and that's the motor effect. But you'll notice that the output of the generator effect and the input of the motor effect are the same. So this is a chain of 3 events. Okay, let's go back to my dropping of the eggs. The reason I dropped the eggs was because my dog ran in front of me. But my dog wasn't just sitting there deciding, oh, you know what, I think I'll run in front of him. My dog saw a mouse. So the mouse caused my dog to run in front of me, and my dog caused me to drop the eggs. It's a series of 3 links in this cause and effect phenomenon. And Lenz's law says that force will oppose the motion. Lenz's law is a really, really amazing thing. So we're going to take a look at a number of demonstrations right now showing you Lenz's law. All right, this is a demonstration of Lenz's law. It's a really, really good demonstration. It's better if you can see it in person. I'm going to show it to you from the view you have here, and then afterwards I've already made another video that shows the top-down view so that you can see what's going on inside. So I have a roll of aluminum foil. Aluminum is a very, very good conductor, but it is not magnetic. And I have a magnet sitting here. It's a spherical magnet. Again, the aluminum is not magnetic. Just to justify to you and prove to you that that is a magnet, if I toss a couple of coins down, they are attracted to the magnet. This is a neodymium magnet. It's a very, very strong magnet. And as you'll see in a video demonstration that I've already recorded, but you're going to see after this one, you have to be very careful, otherwise the magnets can get away from you and you can hurt yourself. So if I were to ask you how long it takes this magnet to fall the distance that that tube is, you could use a kinematics formula, actually, d equals 1/2 at squared, to find out the time. But needless to say, it's a very tiny time. The only reason I have that cloth there is I just don't want to put a bunch of dents in the table. Now, when we drop the magnet through the aluminum tube, as the magnet moves past the different pieces of aluminum that make up the tube, it will cause a current in the aluminum. There's going to be little tiny currents, electrical currents flowing around in the aluminum. But Lenz's law says that those currents are going to produce a magnetic force that's going to oppose the motion. And the magnet is going to be moving down. So the direction that's opposite to down is up, which means there's going to be a force that opposes the motion, and the force will be up. So when I drop the magnet, that's how long it takes to fall through. We'll do that one more time, and then I will show you a top-down view where I point the camera in from the top so you can see what's actually happening. But what's actually happening is the magnet is just kind of floating down very, very slowly as it goes through the tube. So that's one demonstration of Lenz's law. All right, so this is a top-down view. I've got my phone mounted with the camera on top of the tripod, and the phone is in flashlight mode, so it's providing a little bit of light down the center of the tube. I'm going to do my best to keep this hanging vertically, so I'm holding the aluminum tube, and you can see the opening at the top and the opening at the bottom. And when I drop the magnet in, you can see that it drifts all the way down. It's not quite the same as if you were looking at this in person, and that's the one thing about this whole situation that bothers me the most, is there's so much interesting physics stuff that we're getting into in the course that we can't be in person to look at. I'll do this one more time. And if we were in class, I would definitely show you something else right now, but I don't have time to set it up and to make a video. I'm a little crunched for time today, but I will try to make a video where I drop this magnet, and I'll show you the size of it in comparison to this. Ow. Youch. There is the magnet on your left in comparison to the little magnet we've just been using. And I have actually an aluminum tube that will accommodate the size of this big magnet if I can get the little magnet off of it. And I will make a little video showing the big magnet going through the big aluminum tube, and I will post that a little bit later. Anyway, I hope that helps. I need to go get a Band-Aid for my finger, and we'll move on in the lesson. Alright, so the demonstration of Lenz's Law, where you drop the magnet down the aluminum tube, is probably one of the more dramatic examples of looking at Lenz's Law. It's something that is very surprising. Remember that the aluminum in that demonstration is not magnetic, but what's happening as the magnet is moving through the coil of aluminum, it's creating a bunch of little circular currents in the aluminum tube. And the motion is producing electricity in the tube, and that's the generator effect, but the generator effect results in a current within a magnetic field, and Lenz's law says the force is always opposing, so the magnet goes really slow. This is the best way we can come up with to show what's really going on. I've turned things inside out. So what I have are three rods. The one on the left is aluminum, the one on the right is copper, and the one in the middle is some kind of plastic. I'm not exactly sure. Now, none of those materials are magnetic, but the aluminum and the copper are pretty good conductors. And what we also have are ring-shaped magnets. They're inside of a kind of a wooden frame, and the only reason they're in the wooden frame is to keep them from getting damaged if they happen to hit anything. And at the bottom of each of these rods is a little piece of sponge to just cushion the fall. There is very little friction here between the magnet and the rod. But you'll notice that when you drop the magnet over the aluminum rod, it travels slower. And the reason again is that that motion is producing currents. Those electrical currents are occurring inside of the aluminum rod, and those currents are resulting in a magnetic force, and the magnetic force, according to Lenz's law, opposes the motion. So when the magnet is moving down, there's a magnetic force on it up. If I were to drop both of these on the two conductors at the same time, you discover that the copper ends up producing a greater force. And the reason for that is that copper is a better conductor of electricity. So these little tiny currents of electricity that are created when these magnets fall, the currents are greater in the copper, which results in a greater opposing magnetic force. Okay, one final demonstration of Lenz's law. I've made a pendulum. The body of the pendulum is made out of a piece of wood, and at the top I've drilled a hole through the piece of wood and inserted in that hole some Teflon washers to create a very, very low friction pivot point. And then I've put a metal bar through that hole with the Teflon washers and put a couple of clips on the top. And anyway, I've set this up so that if I bring this up, it acts as a pendulum. It swings back and forth. And you could do some interesting Physics 20 questions with this to try to determine the gravitational field strength of the Earth, but that's not what we're interested in. We're interested in the fact that at the bottom of the pendulum are two neodymium magnets, and they're being held there because they're attracted to each other through the wood, but as we know and have learned from experience, magnets can get away from you, causing injury. So as a precaution, I've taped those magnets in place so they won't get away from us. Now I also have two blocks of aluminum, and these blocks of aluminum they're about 3.5 pounds each. It's hard to imagine, but they're very, very heavy. And aluminum is, of course, a really good conductor of electron flow. So what I'm going to do is put the two blocks of aluminum on either side of the pendulum, And we know that when you have relative motion of a magnet and a conductor, which means the conductor can move past a magnet or through a magnetic field, or a magnet can move close to a conductor, we know that what happens is that motion produces a current, that current produces a force, and that force opposes the motion. This is the whole point of this whole discussion we're having today. Lenz's law says the force at the end of this chain of events will oppose the motion. So if I lift this pendulum up and drop it, you discover that it comes to a stop very, very rapidly. And in fact, as I'm pulling this pendulum towards the camera, I can feel some resistance. And if I drop it from this point, it drops very, very slowly. If I drop it from the same height, it oscillates back and forth. But as soon as you have those blocks of aluminum there, you're going to have current being generated through the generator effect, and that current produces a force on the conductor, well, a force between the conductor and the magnet, and in this case that means the magnet's motion is opposed. And it doesn't matter which way the magnet is moving. If I drop it from back here, it still comes to a fairly rapid stop. Okay, again, if we were in person, you could play around with a lot of this stuff on your own, and it really is kind of cool to play around with. In the meantime, though, you do not have any assigned work out of this lesson. This was all qualitative, but you do have assignment number 2, which will be turned in, available to you. So if you go to our shared folder and go into the assignments, you'll see a folder called assignment 2, and the same thing with this assignment applies to all of them. You open up your own individual assignment and you submit it the same way you submitted assignment number 1. I hope you followed everything that went on in that lesson. It's a very tricky set of concepts that we were covering, but in the meantime, you can get to work on that assignment and have a great rest of the day, and we will talk to you soon.